So what I'm going to talk about right now is not really like content. I don't think you really need to take notes on any of this. This is mostly what I want to do is kind of talk about what we're going to do in this course and connect it to some of the past things that you already did in geometry. That being said, I'm going to want some participation from you guys about things that you remember from geometry, which I know is a tall order because it's been some years since that time, but we did this first hour and they did a pretty good job between everyone in the class remembering a lot of the important ideas that I was hoping that they would. So when we look at the word trigonometry, what does the root word look like there? Trig, which you think is probably in reference to triangles. And that's really kind of the fundamental starting place as we're thinking about triangles. So let's imagine back, I know it's a bit tall order the first day of school, to your geometry course, 2 or more years ago. And what are some of the most important triangle-related ideas that you talked about there? Ben? Okay. And when we talk about sine, cosine, and tangent, is there some yeah, that was what I was hoping somebody to say, SOHCAHTOA, which is just a mnemonic device describing how we've defined sine, cosine, and tangent in terms of side lengths of a right triangle. So SOH tells me that sine of some angle is equal to opposite over hypotenuse. CAH tells me that cosine of some angle is equal to adjacent over hypotenuse. And TOA tells me that tangent of some angle is equal to opposite over adjacent. And of all the things that we remember from geometry, this is probably going to be the most useful of those geometry memories. Hopefully we kind of remember SOHCAHTOA. It tends to be a pretty easy one to remember. The acronym helps. So when we talk about opposite, adjacent, and hypotenuse, what is that in reference to? A right triangle. So if this is our right triangle here, and this is our angle X, we'll label this triangle as triangle ABC. Which side is the opposite side relative to this angle X? AC. Good. And which side is the adjacent side? CB. And the hypotenuse would always be AB. Everybody's okay with that idea? Okay. So this is kind of the starting definition that we've given for sine, cosine, and tangent. This is probably what you're familiar with from your geometry course. One of the first orders of business when we start talking about trigonometry in this course is to expand this definition so that we can deal with more than just small values for x. So right now, what values of x can I use sine, cosine, and tangent for? With the way we've defined sine, cosine, and tangent, we can only have values of x between two values. Then, well, 0 is certainly the lower bound, right? The upper bound is less than infinity. It's more than 45. 90. Why does it have to be why does it have to be less than 90? So that's another important piece, is the sum of the interior angles of a triangle is 180 degrees. In our geometry textbooks at Notre Dame Prep, we called that the triangle Sum Theorem, but God knows I'm not expecting you to remember any theorem names, so don't worry about that. So with that idea, if x is an interior angle of a right triangle, x has to be between 0 and 90, right? One of the first things that we're going to do in this course is alter the definition of how we've defined sine, cosine, and tangent so that we can deal with x's of any size. I want to deal with negative x's, positive x's, any positive x, any negative x. I want to be able to deal with all of those. So we're going to alter our definition of how we define sine, cosine, and tangent in order to accommodate that. It's one of our first things that we're going to want to do in extending these definitions of sine, cosine, and tangent being linked somehow to this right triangle. And we're going to extend that so that we can deal with other angles. Is everybody okay with that idea? We won't talk about any of how we're going to do that today, but that's going to be one of the things that we'll spend a good deal of time doing. But I think it's helpful to kind of, see kind of where we're going. Quite positive that's not for us. Yeah, we have many minutes to go. Or not. Class, 12:25, okay. Got it. So 35 minutes. Okay. Splendid. Just still figuring it out. So it's basically the halfway valve. Good to know. All right. So another question here. We've defined sine as opposite over hypotenuse, right? Why not have a function then for hypotenuse over opposite? I hear some people mumbling. I'd like to be able to hear the mumble, so they could be really good ideas or really good answers. I'd love to hear them. Megan? Don't.
Okay, never mind. Next person.
Okay. Well, let's get back to that because I think I know where you're going. Okay, so if the hypotenuse is the longer side, what does that mean if it's the numerator of the fraction? What can we say about that fraction if the hypotenuse is always at least as big as the opposite? Great. It has to be greater than or equal to 1, right? If it's at least as big as the opposite. And specifically, what could that mean then? Not only could it be just greater than or equal to 1, how big could it get? Infinite, right? If the if the opposite side is close to 0, that's going to make the hypotenuse, or the ratio of hypotenuse to opposite, massive. Since the hypotenuse is bigger, if you have bigger over close to 0, that's going to bomb off to positive infinity, right? What would that look like graphically? Very vertical. In fact, it would be a vertical asymptote, right? If that's approaching positive infinity like that. And we saw some other functions in our Algebra 3-4 class that had vertical asymptotes. Do we remember any of those? There are 2 specifically types of functions. From what? So not a quadratic. They didn't have a vertical asymptote on there. Bridget, what was that? Rational functions was one of them, right? All those rational functions had vertical asymptotes, or almost all of them did. The other was, well, inverse functions wasn't a specific class. We didn't talk about, did you say irrational? That's not a thing. That's okay, though. Like, make your guesses. Like, no penalty for wrong guesses. Starts with an L. Not linear. That's okay. It was a second semester topic. It was logarithmic. All logarithmic functions have vertical asymptotes, which is because they are the inverse of what kind of functions? Exponential, that all have a horizontal asymptote, right? So that's good. And it turns out that there is really no reason that we can't define another trig function that is hypotenuse over opposite. And in fact, we'll do that in trigonometry. We'll define 3 more trig functions that we'll call the reciprocal functions, that are basically hypotenuse over opposite, hypotenuse over adjacent, and adjacent over opposite. There's really no reason that we select these particular ones, other than, for sine and cosine particularly, the range of the functions is very convenient. What can we say about the maximum value for sine and cosine? Think about the relationship between opposite, adjacent, hypotenuse. Which one is always the biggest? Hypotenuse. So what are opposite over hypotenuse and adjacent over hypotenuse always going to be less than? 1. I should say less than or equal to. But yes. So that's probably the only reason why we've selected to make the ratios in this way, is because the outputs for sine and cosine are bounded in a way. And if we did the reciprocals, they are unbounded, which is maybe inconvenient to deal with. And our mathematical ancestors were not fans of infinity. So they had problems with that. Okay? Everybody feeling okay? Again, we're not dealing with content. Anything that I've kind of hinted at again here, I would be redoing in much greater detail later this semester. We're just trying to get a feel for what kinds of things we should remember, specifically these geometry topics. And you guys have been doing a pretty good job so far. Some other geometry topics related to triangles here. Could be facts, could be vocabulary. Ben? Okay. Okay. So I think what Ben's talking about is when you have 2 parallel lines cut by a transversal. So if we name these angles 1, 2, 3, 4, 5, 6, 7, 8. So like angles 1 and 5 are what we call corresponding angles, because they're at the same position of the x made by the transversal. Those angles are congruent. Angles 3 and 6 are what we call alternate interior angles. We say they're alternate because they're on opposite sides of the transversal, but they're interior in that they're both in between the 2 parallel lines. So those are congruent. And then we have 2 and 7 that we call alternate exterior angles. Again, alternate because they're on the opposite sides of the transversal, and exterior because they're on the outsides of the 2 parallel lines. Those are congruent. And then we have one more relationship. Angles like 4 and 6 are consecutive interior or same side interior. I think I've seen it written both ways. And the sum of these 2 angles is 180 degrees. And then there's some other relationships you can build that are just, built out of these 4 fundamental relationships. But that's, I think, is probably where you were going, right? No. And this could be important when we do some proof things later. Hi, come on in. Thank you. James, this is for you. But it's not directly related to what we're going to kind of start with in trigonometry. What else do we have here? Yes. Good. So some of you might remember this from geometry. You would have spent a little bit of time talking about the law of sines and law of cosines and doing some problems related to those. If you're like, it doesn't really sound familiar, it's because it was like 2 days from a class that you took, like 2 years ago, in the second semester 2 years ago. So if you don't remember those, that's okay. We'll start. This would be a topic I would assume really minimal prior knowledge on in this course. But these are certainly 2 things that you probably talked about in your geometry class. If you took the honors geometry class at Notre Dame, I know you talked about them. If you took a different geometry course elsewhere, you may or may not have seen that topic before. But yeah, that's certainly something that we'll talk about, and you may have seen that. Related to the law of cosine specifically, there's something that we haven't talked about yet that's a really fundamental idea with regard to triangles. That's the one I was hoping for, yeah. Absolutely. Which is a squared plus b squared equals c squared. But not all the time. It has to be under a specific circumstance. What do we need to have for this to work? Yeah. In a right triangle. Now, what do the A, B, and C represent inside that right triangle? They're sides, and they're not any sides, right? What do they have to be? C has to be the hypotenuse, and A and B could be either leg. It doesn't really matter which one you call A and B, but C must be the hypotenuse. It turns out it would be nice if the Pythagorean theorem worked for non-right triangles as well. That would be nice, wouldn't it? We do have a version. It's the law of cosines. It's the Pythagorean theorem for non-right triangles. It includes a little bit of a fudge factor to correct for the over or underestimate you're getting with the Pythagorean theorem at the end. And we'll talk more about that when we derive the law of cosines later in this course. But if you can remember that it's basically just the Pythagorean theorem with an extra little fudge factor, I think that's often helpful. And that fudge factor becomes 0 in the instance of a right triangle, because a squared plus b squared does equal c squared. Good. And let's think, is there any other big triangle top? Yes. Yeah, that's a good one. So we have 2 special kinds of right triangles. There's the 45, 45, 90 and the 30, 60, 90 triangles. So the 45, 45, 90 triangle is special because the side lengths exist in a special ratio. So that ratio is the legs have length x, and the hypotenuse has length x square root 2. A 30, 60, 90 triangle does anyone remember the ratio of side lengths here? Oh, I still have it on the board. I'll just write them down then. The short side is x, The longer leg is x square root 3, and the hypotenuse is 2x. The way I remember that is that the square root 3 goes right next to the 30. And then it's easy to fill in from there because you know the hypotenuse is the biggest one and 2 is the biggest of the numbers 1, square root 3, and 2. So those will be really important for us. A lot of what we'll be interested in this course is the exact values of sine, cosine, tangent, etc. So what do I mean by an exact value? Something like the square root of 2 is an exact value as opposed to 1.4, which is an approximate value. Everybody okay with that idea? So if you remember, when you've used sine, cosine, and tangent in your calculator, you do like, sine of 36, what kind of number do you get? You get a crazy long decimal, right? You're getting an approximate number. In all likelihood, the sine of 36 is probably an irrational number that can't even be written as neatly as a fraction. We're going to be very interested in the ones that we can write exactly. And those values, or those angles that we can find an exact value for, correspond to multiples of 30, 45, 60. So the angles, the acute angles in these special right triangles. So those will be ones that you'll probably want to have those triangles memorized. It becomes pretty useful to have that information memorized. As you can, it's, I think, easier than trying to memorize like the unit circle or something, which we'll talk about what that is later on. Some of you might know already, and that's great if you do. If you don't, I don't assume that you did. But those will be useful for us. That's very good. What else? There's probably some vocab, right, that's related to describing triangles. So things like isosceles, and I apologize in advance for spelling this wrong, obtuse, scalene, acute. I mean, there's right, equilateral, and probably along that same vein we can write equiangular. Everybody kind of vaguely remember these vocab, or at least look familiar enough. What does isosceles mean? Two sides are the same length. Good. Obtuse has an angle greater than 90. Can I have two angles that are greater than 90? Impossible. Why? Because that would be greater than 180 degrees in that triangle. Very good. Scalene, what does that mean? None of the sides are the same length. Acute, all the angles are less than 90 degrees. Right means you have one 90-degree angle. Can you have more than one 90-degree angle? No, because you must add up to exactly 180 degrees, and you can't have a triangle with a 0-degree angle in it. Equilateral, all three sides are the same length. Equiangular, all three angles are the same length. Is there a difference between equilateral and equiangular? What do we think? They are equivalent statements. So if you remember, there is a theorem from geometry that says that the side length opposite the angle is proportional to the angle. So if these three sides are all the same, those three angles would have to be all the same, and vice versa. So equiangular and equilateral could be used interchangeably. They both convey the same information. Probably equilateral is the much more familiar term. But they are ostensibly describing the same triangle. Okay with that idea? The small difference being, if I know the triangle is equilateral and the side lengths are 3, what do the angle measures have to be? 60. If I know it's equiangular, the angles have to be 60. Can I figure out what the side lengths are, though? No. So typically we describe triangles as equilateral because it conveys both sets of information. You know both the side lengths and the angles. If I say equiangular, I don't know. I can't say anything about the side length, other than they're all equal, but I can't say anything about the numeric length for that triangle. Okay with that idea? Let's think here. We still got some minutes to do a little bit more here. So we have a triangle. There's some special segments that we can draw for a triangle. If you remember back to geometry, there's 4 different kinds of segments. So you can have like an angle bisector, right? You could have a median, which connects like vertex to midpoint. You can have a altitude, which goes from vertex to opposite side and intersects at a right angle. Maybe I should just draw that as a solid line. Shoot. What's the other one? Does anyone remember? Can't be that important if I can't remember it, right? Oh, it's the perpendicular bisector. That's right. So the question is, when are all those segments going to still be the same segment? What kind of situation, what kind of triangle do we need to have for all these? Yeah, equilateral. In an equilateral triangle, all of those special segments are the same. Is there another triangle where sometimes those are going to be the same? In an isosceles triangle, everything involving this angle, those segments would be the same. So drawing the median, the perpendicular bisector, the angle bisector, the altitude, from that angle will all be the same. All the other situations are not going to be the same, which makes subdividing like a non-right triangle into two right triangles very difficult. Right? If I try to do that here, the problem is I don't know how long those two separate segments are because it's not that altitude doesn't bisect that side. Furthermore, I also don't know what those angle measures are going to be because that altitude isn't going to bisect those angles. So it would be nice for us to have a way to use sine, cosine, and tangent for non-right triangles. And as noted earlier, look, I flipped my page too soon. Give credit where credit is due. Abigail, we can use the law of sines and the law of cosines in situations where we have non-right triangles. To use SOHCAHTOA, we have to have right triangles. Everybody okay with that idea? All right. So again, any kind of content we've talked about here, I would be redoing when we talk about these things formally. I just wanted to connect some of these geometry ideas back to what we're going to be talking about in the future and just rehash some of these things that were important ideas from geometry and a little bit of the important relevant vocab from geometry. There's a bit of algebra 3-4 topics that will also be kind of important. Most of these have to do with what a function is, or functions themselves in general. Does anybody remember the definition for a function? Yes, Kayla. Okay, I would need it to be just a little bit more specific than that. Exactly is the missing word. Yeah, you'd have to have exactly one y. So we're basically just pairing sets of x's with sets of y's to make ordered pairs, x, y's, where each x pairs with exactly one y. Okay. And in the beginning of our attributes of our Algebra 3-4 class, we talked a lot about like ways to describe a function or attributes of a function can have. So we talked about one of those already briefly. Functions can have asymptotes. We talked about vertical asymptotes a moment ago when we discussed why we might not have wanted to use hypotenuse over opposite as opposed to opposite over hypotenuse. So some other ways to describe a function or attributes a function can have. Okay, so you're talking about discontinuities, like a removable discontinuity. And an asymptote is a type of discontinuity. We call those typically infinite discontinuities, but we can also have removable. We saw that when we talked about rational functions. Ben? Okay, so let's just call that generally key features. So things like a vertex or a maximum and minimum. So we can talk about maxes and mins. When we talk about maxes and mins, there's another thing that we often are interested in as far as an attribute. Increasing and decreasing. Remember, when a function is increasing is basically where you can walk uphill along the graph. The slope is positive over that part of the function. And it's decreasing where, like, if you're walking along the graph from left to right, you're walking downhill. You guys that had me last year, remember the little man walking along the graph? We talked about that. And there's one other part that goes along with increasing, decreasing. That's where the graph would be constant. The graph would be constant at the top of the hill or the bottom of the valley, or any place where the graph is flat would be what we mean by constant, where it's not increasing or decreasing, it's just staying the same. Okay. Let's see what else. We talked a bit about concavity. So we say a graph is concave up if like it was able to catch water if you're pouring in it. So this would be like concave up. Concave down would look like this. If I poured water over this, the water would run